So electric field, we start from a positive charge and the field lines supposed to go omnidirectional, meaning they go in all directions. These are called the field lines and represented as a vector. So for ease or convenience, we assume that it is a charge is placed at the origin O, and then we start drawing if the line is longer, the field strength is more. If the line is shorter, the field strength is less. Like that you draw in all directions. So these are all imaginary lines. They are not seen. We only draw them, just like the magnetic field lines. They are all imaginary lines. So two things. One is they are imaginary. That means we have drawn them. So one person may draw 20 lines, another person may draw 100 lines, another person may draw a million lines. Okay, so the lines exist. In fact, it's like a light also. If you draw a light ray from a bulb, it will go in all directions and million lines will be there, million rays will be there. But for simplicity, we draw only few of them. So these lines are imaginary and they do not intersect each other. They do not intersect each other. These are the two characteristics of the electric field lines. Who gave these things, this model, and the person who gave was Faraday. Okay, so Faraday has provided these electric field lines. They don't ask this question, who had given these lines and all, and they don't even ask, but there's 2 points like the imaginary and do not intersect. They may ask. Okay, so that is about the electric field lines. So he has given almost 2 pages in your textbook. Page number 23 started and has gone to page number 24 also, and then further on to the picture given at 1.16. He has given a picture there and indicated saying that all the lines are going, and then if you put some area like that, okay, he has put that into blue, blue shaded area. Okay, so these lines, it's like a bunch of lines going through area. It's something like a traffic going on a specific road, the number of vehicles going on a road. Okay, so this area is, if you take a small piece of area inside that, we represent that with the delta S. S indicates area, delta indicates a small area. So why do we need this particular description? When we go to the next page at the electric flux, he will be giving out at page number 27, he gives out an expression for electric flux. Okay, that's the reason he introduces that the number of lines, assuming that just like the way we catch hold of our hair, right? So we can say that so many hair is there, so much hair is there in our fist, in our hand. Okay, like that, in this small area, if you have so much of electric field, okay, so if you know that electric field is going through this small area, then we give that flux equal to electric flux, that means a bunch of lines going through, equal to E, this is a vector, dot delta S, this is also a vector, both are vector, and this is called a dot product. This is covered in a vectors, mathematics vectors. Okay, dot product of two vectors, and that will give you phi. That means how much of the electric field lines are going through this area. So that is about the electric flux. So they can ask, what is an electric flux? Okay, so these two pictures, this formula and this picture, we need to see the number of electric field lines going through. In fact, this is a sigma of E dot ds. Okay, sigma indicates that all the electric field, it can be due to all the charges, all the components of the electric field. Okay, so that's why they give E is a vector, delta S is a vector. So you just need to represent this in the form of a formula and need to be writing what is an electric flux. Any question? Any question? No? No, right? So then look at the picture Uh, this you actually get we cover that in a mathematics, right? We have a vectors and a 3D. Inside 3D, at that time we will be talking about for every plane. Let's suppose this is a plane. There will be an equation. The equation of the plane actually will be represented by the normal to the curve. Okay, this is called a perpendicular or normal to the curve. Okay, so at that time we will be learning maths. That's the reason if you look at the pictures on page number 26, he draws one rectangle and there is some mango like a picture, and then he has drawn something upwards. Okay, so yeah, this entire thing, this area is represented by the delta S. That's the reason they give the picture there. Okay, so from that concept we get the formula saying total phi is actually, if you take only the small area, if you take the small area, for example this area, and this area is delta S in a big sheet of paper, okay, this small area, then delta phi equal to E dot delta S. E dot delta S. Okay, if you want a total phi, that means sigma of delta phi 1 plus delta phi 2 plus delta phi 2 phi 3. That means what? So many areas, small areas if you are taking. Okay, that is what the sigma. Okay, then you get sigma E dot ds. Both are vectors. This is at equation 112. This is the total flux going through a surface. Flux through surface, that's what they call it. So it is essential to remember this formula. All right, now we are going to the third topic, which is important thing called a electric dipole. So if you read the first line, electric dipole is a pair of equal and opposite point charges. So I'll write that in the next page. Okay, it's electric dipole. Actually this pole and all comes from that knowledge of North Pole and South Pole. Okay, so that's from there actually we get this word. So there are two poles for the earth, one is the north and the south, and both are opposite. The second place we hear about the poles is in the magnet. So we say that magnet has got a north pole and south pole, and then if you bring another magnet with a south pole, they attract, right? So they attract. So let me just, because the line is from north, it will go. Okay, so in the electric dipole case, you have a positive charge and you have a negative charge. So wherever you see both charges, say Q1 and Q2, okay, if they are equal, Q1 and Q2 are equal in their charge, and they are opposite in polarity, and then separated by distance. Obviously they are separated by distance d. Then we call that as a dipole. This entire thing we don't actually make it as a picture, and this is a dipole formation. This dipole is important concept. It works even in a chemistry also. Okay, when there is a covalent compound formed, then there is a polarity dipoles. Okay, in atom you will have a dipoles also. Understood, right? So it was a concept. It is there both in physics, chemistry, everywhere. Okay, so they'll ask what is define electric dipole. Okay, I'll give you the short questions and all for the entire question bank for physics, right? All short questions and answers I'll give you after the end of the chapter. Okay, right now we will first go through trying to understand. Okay, so you will have a question like define an electric dipole. So this is how the question comes. Then the answer is there. First two lines you can underline that. An electric dipole is a pair of equal and opposite point charges. Every word is important there. We have to say pair. We also have to write the word equal. We also have to write opposite and also say point charge. You ask anything, I can tell you why it is point charge. There are different types of charges. There can be line charge, there can be a volume charge, that can be an area charge also. That's the reason he wants to say, just like a geometry, there's a point, there's a line, there is an area, there is a volume. Okay, so in the charges also you can actually tell them like that. So we can actually specify like that. Therefore, this particular thing is a point charge. That means the dimension is very, very, very small, tiny. Okay, so and they are separated by a distance. For example, and this distance, he calls this distance, right? This distance is 2a. This is a fixed one. Okay, they keep telling this word is a 2a. They are separated by a distance 2a. So what is a? Like x, we don't know. They are separated by some distance. Okay, they are separated by some distance. Good question. Because in derivations and all, we have to take half of the distance. Okay, so if you take a, and then you want to consider half of the distance, you'll get fractions, a by 2 like that. That's why for convenience sake he puts as a 2a. Okay, so if you remember, for example, you have an equilateral triangle. Okay, I'm answering your question. Okay, you have an equilateral triangle. So each side is, for example, a. Then if I want to find out the area, right? So when I draw perpendicular here, that divides this into two halves. This is a by 2, this is a by 2. And I want to find out this total area. How do I do? I'll get the area of this one multiplied by 2. How do I get this area? Half into base, which is a by 2, because for this triangle it's a by 2, multiplied by height. How do I get height? We have to again do the Pythagoras. Half into a by 2, the square root of a squared minus a squared by 4. Then you get half to a by 2 into, this is root 3a divided by 2 you will get. So this is 4 is there, that's why you get 2. Okay, so you are getting a square. So half root 3 by 4 a squared. Understood? This is for this shaded area. So you want to do for the total. So total triangle area equal to 2 times of this. Therefore root 3 by 4 a square. See, now if you consider this, you got a fraction here because we consider as a. Let's suppose we take it as a 2a. Each side is 2a, 2a, 2a. Then what happens here in this, you'll get half into 2a, the half of this is a, into root of 4a square minus a square. This is a, right? That's why a square. So you'll get straight away half into a into, this is root 3a. So straight away you will get in terms of a, whereas this comes in terms of, because of the 2a. So this is convenient because you will have to do every time this fraction. That's the reason they take a 2a. Clear? So I'm erasing all this stuff. Okay, so you'll go back to this page. Yeah, this is page 4. So that's the reason we talk about phi is equal to this, and then we have electric dipole. So the midpoint of the locations of minus q and plus q is called the center of the dipole. So now I am formally writing. So dipole, there is a minus q and this is plus q, and there is a center, and this is called the midpoint is called the center of the dipole. Center of the dipole. Okay, this is a virtual, like our own imagination. You can't physically see a dipole there. Okay, in any field. Okay, so and this distance is 2a. This is required for the derivation. The derivations what we will be doing, we need this particular thing. Okay, now look at that paragraph, second paragraph. What he says, the total charge of the electric dipole is obviously 0. Why? So this fellow, this plus q, creates a field something E plus. This minus q also will create E minus. So their magnitudes are same. Both are vectors, right? This fellow, the field from plus q will be this side. This is E plus. The field for minus q, right, has to be entering into that. Okay, so it will be entering into here. So here the field is going out, here it is entering. Okay, so if it really coming this way, the field, then the q would be pushed up. Since both are equal and opposite, they cancel. They cancel with each other. Understood? Yes. Okay. Okay. Now, yeah. See, if there is electric field is from a positive thing, it will be going outward like that. If there is a minus charge, electric field will be entering. This is a notation. Electric field will be entering. Okay. So, in this case, hello, you are able to hear? So, here the field is entering into minus q, the field is leaving plus q here, right? So, the field entering here need not be from this plus q. Understood, right? This can be actually around like that. So, we only consider the line which will be entering exactly opposite this way, okay, and the one which is coming from here. This is coming from plus q. This is coming from another plus. Understood, right? So both of these are equal and opposite. These fields are equal and opposite. Therefore, they cancel each other. Right? In fact, what this picture I'll erase. This picture, I think this picture I'll erase. You keep this one. This is whatever you have here, right? This is the correct one. So from minus q, right? This is a minus q. Okay. So field vectors, actually field vectors you should say, field vectors are equal and opposite, and therefore they cancel. So this is about the electric dipole property. Okay. Now if you are going into the second paragraph, the total charge is obviously 0. This does not mean that the field of an electric dipole is 0. The total is 0. But then this doesn't mean that this dipole doesn't create a field. This creates field around this, and all the lines will be coming towards minus q here, plus q, it will be going up. Okay. So the electric field due to, since the charge q and minus q are separated by some distance, the electric field due to them when added do not exactly cancel out. However, at a distance much larger than the separation of the two charges, r is much greater than 2a, the fields due to plus q and minus q nearly cancel out. So you don't need to write all that stuff. Okay. The electric field due to a dipole therefore falls off at a large distance faster than like 1 by r square or whatever. Okay. So we will be talking about this in the next derivation. Okay. So the second paragraph, only one line that is required. The total charge of the electric dipole is 0. Got it? They cancel out. The cancel out and 0. That's what we need from the electric dipole. This is all for 2 marks. Whatever they had asked for the electric dipole, define electric dipole or represent electric dipole and distance 2a, all the things are for 2 marks. Right? Okay. Now it's a derivation. Okay. What I have to do is I will be writing down each step by step. Okay. So there are 2 parts to the derivation. Both the parts they may ask as a separate, or they may ask sometimes as a single one. Alright. Okay, the picture what I have drawn is given in the 28 page number 28. At the top there is A and B. In the under A they have given the same picture whatever I have written there. Okay, then there is another one which we need to talk about from the dipoles. That is called dipole moment. Another word is a dipole moment. So this is also famous 1 mark question. So the dipole moment is represented by letter P equal to whatever is the charge multiplied by 2a. You can remember this like this, or so dipole moment P is equal to charge multiplied by distance between the charges. This is called a dipole moment. Okay. Now to talk about what is the field of an electric dipole. So what he is trying to say is that let's suppose you have some minus and plus somewhere, then there are so many places here, 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 here. You have different points if you take P1, P2, P3, P4, P5, P6. So in fact at each place the electric field intensity, that means how much is the intensity, one should be able to derive that. Okay, so that is what in a simple form what he will be talking about is if you have an electric dipole with a plus q and minus q. So this, yeah, so you have minus q and plus q. We just want to see if I keep anywhere on this line. Okay, if I keep anywhere that point P is here, or point P is here, point P is here, this is point P. So how much would be the electric field on this line, any point on this line? That is one case. The other case is on exactly perpendicular between these two. Point can be anywhere. Okay, these are the two cases we will be doing the derivation. So if you look at the first, he says for the points on the axis. Now what does it mean by the axis? Okay, you heard of cylinders, cylinder is known, right? Cylinders will be like this. Okay, cones will be like that, right? So if you draw a center line like this, right, this line which goes to the center is called axis. So for this is axis. Got it, right? So that's called an axis. So in the similar way, now if I have a dipole, this minus and the plus, the line joining these two is called axis. Okay, so the other one which is perpendicular, right, that is called equatorial line. If I draw a perpendicular line, perpendicular bisector like this is called a equatorial line. So now we have two cases. If the point P is anywhere on the axis, so P can be on axis. This is case A. Case B, P can be on equatorial line. So these are the two derivations. Sometimes they may just ask the second case, they'll ask. First case is very easy, so they don't ask the first case most of the time. Either they ask full or they ask B. Calculate the electric field intensity or the electric field of a dipole. You need to remember that this is of a dipole, okay, clearly, right? So when they ask electric field of the dipole, on at any point on the equatorial line, then we have to do all this derivation. All right. Okay. Now so if you go back to find what is the equation for E, electric field, if you look at that, that's 1 by 4 pi epsilon naught into Q by R square. So that is what you will have, electric field. So I'll give that one more time. So electric field due to a charge is given by 1 by 4 pi epsilon naught. Okay, that's the one, and this is E due to a charge Q. Okay, Q divided by whatever is the distance. Okay, so that's the distance is R square. Okay, so in fact, if you remember that example, it is basically you have 1 by 4 pi R only, not R square. Go back to electric field, you will see 1 by, because it's like E is equal to F by Q. I said F equal to that 1 by 4 pi epsilon naught Q by R square and all the stuff. Okay, so you will have this, and when I am writing this, we will say that in the case A, that means we are talking about minus and plus, and we are talking any point on this line axis. So we consider a point P. Okay, we consider a point P, and this distance is R. This distance is R. Oh, sorry, the distance is 2a. The distance is 2a. They are separated by 2a always, and at a point R. So we just want to say that at a point R, if you look at that description on that line, right? I'm talking about 1, 11, 1. I'm talking that 4 points on the axis. That A, first one I'm doing. Let the point be at a distance R from the center of the dipole. So we are considering this point P. This is the center. From here to here, it is R. Okay, so now there are two cases. One case, the center of the dipole on the side of the charge Q, that's one, case 1. There is another case which is between minus Q and Q. Okay, so both cases are there. One case is after outside case, one case is between them. This case is now its P is outside. Okay, this is outside this dipole. So if you want to calculate, this distance is R, this distance is R, and this is A. This part is A. So from this plus Q, if you are considering, the distance is R minus A. Distance will be R minus A. If you are considering from this to this point P, okay, this entire R plus A. So you will have R plus A. So you are saying the distance will be, in one case it's R minus A, another case R plus A. Therefore E will be, okay, 1 by 4 pi epsilon naught Q divided by R minus A whole squared into this moment. We talked about moment, right? Q into 2A. Okay, that's the one. In the second case, it will be R plus A whole squared. This is because of this distance plus Q. So the next one will be E of minus Q. E of minus Q due to minus Q, 1 by 4 pi epsilon naught Q divided by R plus A whole squared into P. So you got two expressions. The picture, if you would like to see, there is exactly what I have written with the arrows he has done. That's it. Okay. So now the total field total field at P due to the dipole equal to E plus Q plus E minus Q. You have to add both the things. Then when you do that, you get 1 by 4 pi epsilon naught QP. In both cases it is there. Then you will just say 1 by r minus a whole square. I have taken the common already. 1 by r plus a whole square. This is what we do. Okay. So that gets simplified as, so we have to do the simplification. You get 1 by 4 pi epsilon naught into Q into P. This one will be r plus a whole squared plus r minus a whole squared divided by, okay. So now the question, you will have to think about this. I will come back to this. Okay, divided by r minus a into r plus a, which is r square minus a squared whole squared, because I multiply the inside ones and I put the square to the top. Okay. Now the question is, we said both are equal, but they are in opposite direction, right? E plus Q and E minus Q. Therefore, I have to take one of them to be negative. Correct? Hello? Hello? You are there, right? Yeah. So that's why this thing should be minus. So that one becomes minus. So you will have r minus a whole squared, and then this is r plus a whole squared become minus because one of them is a negative. This is to be considered negative. Okay. You can write as is in exam. Okay, the plus becomes minus, and therefore this is minus, this becomes minus. So this is a plus b whole squared minus a minus b whole squared. So when you actually simplify, this part becomes this part, right? This becomes 4ar. Okay, that part is what I am simplifying and writing in the next page. So E equal to 1 by 4 pi epsilon naught to Q into P within the bracket. Now you get 4ar divided by r square minus a squared whole squared. Here they do the simplification. What simplification they do? For example, okay, let's suppose r equal to 1000, a is equal to 2. I am giving an example. So 1000 square will be 1 followed by some 6 zeros, 4 5 6 zeros. A square will be 4. R square is this, a square is equal to 4. And do you know what will be r square minus a square? You are subtracting 4. You know, it's something like, you know, someone loses 4 rupees from 1 million rupees. 1 million means 10 lakhs rupees. Does he bother about that? From 10 lakh rupees, he just loses 4 rupees. I mean, of course, if he's not a stingy person, you know, then it's a 4 rupees, no problem. I'm still having 10 lakhs. Correct? So this all r square minus a square will be almost equal to r square only. So what it means is, if r is much greater, this means much greater than a, then we ignore that a square in the denominator. So that means the denominator now e becomes 1 by 4 pi epsilon naught into q into p into 4ar divided by r square. So 1 r gets cancelled and 2 gets cancelled. Okay, and this 4 gets cancelled, this 4 gets cancelled. Okay, but then he keeps like that, like 4 QAP, like that only. They don't cancel. Sometimes they cancel also, they don't cancel. Both mean same. Okay, so the first part of the derivation is over. All right, now we have to go to the second part of the derivation. Second part of the derivation, you will have to see the picture. Okay, that picture I will draw. So this is the second part. E at point P on equatorial line. So for this I put this minus and plus, and I write these lines here like that. I draw this distance as 2a. So somewhere on this perpendicular line you got a point P. This is a point P. Okay, so let's assume that this point P is at a distance. That means this distance is r. And now this is what we know, this is r, and this part is a. Clear now? This same as that equilateral triangle I have drawn. I just erased that, remember? Similar. So this is 1 and this is 1. What is this? This is the distance we need to calculate for E plus. Because of this charge, what is the field here? So this will be in this direction. Because it's plus, right? The field direction will be like that. Understood? Not understood? So if you look at the diagram in the textbook, he has taken minus q there. Shall we take minus q without having a problem? So let me take minus q, otherwise you'll get confused on this. So he takes plus q here and then minus q here, and this distance is 2a, and the point P is on equatorial line, and this is r. So we have like that, and since this is minus q, this is minus q, right? So the field will be coming into this. The direction will be like this. Okay. So let me draw a line. Drawing a line is this one. Okay. So from P, it will be like that, and from here it will be like that. Okay. So in fact, it is this field will be, this is a vector, okay, it will be like that, going positive like this. The electric field lines we started right in the beginning, whereas this one will be coming to the minus q. It is like this. Okay, so if you consider the resultant of these two vectors, the resultant of this vector and this vector will be somewhere here. It will be going like that. This is called a E resultant. This is E plus q. This will be E minus q. So now in this derivation, we have to write down what is E plus q, and we have to write down what is E minus q, and from there we have to come back to our derivation, final derivation. Okay, so the final derivation, the last expression for this is 1.18, equation 1.18. Only the 3-4 lines I will be talking about, right? So most of the people will get scared on the derivations. That's why I'm doing it slowly. I can do it very quick also. Okay, now when I am talking about this distance, this is a small a, this is a r, and this is an equilateral triangle. Therefore, to calculate E minus q, for example E minus q, you will have same 1 by 4 pi epsilon naught into q divided by this distance, right, is nothing but square root of r square plus a square whole squared, because we need a q by r square, right? Understood? Yes or no? Understood, right? So we just need to be taking this part like that. Okay, or in other words, if I am doing this whole square, I will get E plus q, E minus q would be, in this case also same thing. Okay, in both the cases you will have E plus q and E minus q, you will have q by 4 pi epsilon naught into r square plus a square, because the square root will cancel with this. So both will be same, and this is what the directions are. So as I said, if I have to talk about how do I get this resultant, okay, the total electric field, you see that, right? E, they have written E is equal to E plus Q vector plus E minus Q vector. So here is the important part here. He puts an angle, okay, so cos 0 or something like that. You see that cos theta is there, right? That's a cos theta actually, okay. So if there is a cos theta, that means the angle between them is a cos theta. So here we need to find out the component of this would be like this, the component of this would be like this onto this. So components of these two along this center line. So if you are assuming that this is some theta, okay, this is theta, this is also theta, this is also theta, and this is also theta, okay. Then what happens, we are taking E would be first part E minus Q cos theta, okay, then E plus Q cos theta. This is what the components are to be added, okay. So if you look at the expression 1.17, he gives that E is equal to E positive E negative multiplied by cos theta. You read that there, correct? Yeah. So finally what we have to do is that you write that in a simple way. It is 2qa. You are putting the 2qap because we want to talk about the dipole moment. That's the reason we call it as a 2qa, and because of that you write that it's 2qa p bar or pq. So at large distances what happens, okay, how I am getting this 2a? If you look at that, how I am getting this 2a, right? 2a is nothing but the distance between them. If I have the distance between both, the total electric field is opposite to P. What is this opposite to P? P is a dipole moment. Dipole moment direction whichever is there, and it will be opposite to that. Okay, so that's the, so we got the expression already. That's the final expression was over. Now we talk about the relation of E and P in a equatorial case. In a equatorial case, so E is opposite to that of, this is also important point, that's why I'm writing it, okay, opposite to that of V. So in when you have this plus and minus like this, okay, so if I have minus here, which side would be the P direction? P direction should be so this plus q and this is minus q, okay. So this should be along, but it will be in this direction, P will be in this direction. Therefore whatever E you have got, right, will be in this direction. You look at both are opposite, these are opposite direction, okay. That's what they mean in the picture. If you see, right, he has put E at the top, okay. P direction is given arrow towards left, okay. So this is an important point. E is always opposite to the dipole moment. And now the final expression what they have written is when R is much greater than A, obviously A square is ignored, okay, A squared ignored. Then what happens, you will have E is equal to 2qa divided by 4 pi epsilon naught r square plus a square to the power of 3 by 2, that's automatically becomes r cube. You need to remember this. Don't get confused between here we got r square, right? You understand? Here we got r square. How it became r cube is because we are multiplying this entire thing with a p. Because of this p, okay, that's how you got another square root and another r cube. Okay, so only thing, that's the reason I am highlighting it. Previous case it was r square, here it's r cube. So that's the derivation. Okay, let me first stop for a while, okay, then ask you